All right, so we're recording again. That's good. All right, I see Chris sitting there. That's good. We'll give people a couple more minutes and then intro our next speaker. All right, I vote we get started.
Okay, should I?
Go for it.
Okay, so our next speaker is Christopher Griffith. Christopher graduated with a PhD from Penn State in 2015. He was a postdoc at the Naval Research Lab, NRL, for 1.5 years, and is currently an engineering specialist at the Aerospace Corporation. So with his talk, we're gonna get to be tingly astronomers who are hearing about space stuff again. Go ahead, Christopher.
Yeah, that's right. Yeah, do you want to stop sharing and then I'll share?
Exactly, but my cursor. I'm almost there. Let me do. There you go.
All right, thank you. Okay. Yeah, so that was an older picture of me. That was fun to see, my giant hair. Okay, so I'm going to talk about sort of a guide to working in the aerospace industry. So switching gears a little bit from the data science, although as you'll see, we do a lot of that in the aerospace industry, as does a lot of other disciplines. So as she said, I'm an engineering specialist at the Aerospace Corporation. I've been there for about 5 years. I really like it, and I'll sort of give you an idea of sort of what problems we're working on and where you can fit in. And it's basically anywhere you want, as you'll see. So before I start, my talk, I just want to say my company, Aerospace Corporation, is hiring. We do a lot of really cool stuff. You can see on the bottom left there, we actually do have telescopes we work with. That's at our campus in El Segundo in LA. Our other main campus is in Chantilly outside of DC. But we also have locations all over the United States. I'm at the Albuquerque location. Colorado Springs is another one. All kinds of stuff. We do a lot of basically anything in aerospace industry we do. So look out for us and keep us in mind. I'll flash up my email and all that stuff in a bit. Another thing I'll mention too is we do accept graduate level interns. So if you're still in grad school and you're not sure what you want to do, you can come work for us for a summer. We also do undergraduate interns as well. So something to keep an eye out for is, to just sort of dabble in if you don't want to make the leap. And then this is that's my email at the bottom. I'll flash this up again at the end. And there's a QR code. I think it links to some of our jobs and articles and things. I'll flash that up again at the end. So don't worry. So just an outline of the aerospace industry, right? I'm just going to talk about the who's who in it. who the government is, who the contractors are, and then what's called an FFRDC, which I'll explain a little bit later. Just give you an idea of who the employers are and sort of where you could fit in and what sort of roles you would have in each of those companies or different types of roles that you'd see there. I'll then just talk about a case study, right? So just to sort of outline the problems that we're looking at in aerospace and sort of who does what, where the technical comes from, and sort of give you an idea of the problems that we're looking at right now and how you could fit in. And then at the end, I'll just talk about little things of, where you can fit in. Again, it's going to be basically anywhere you want, but just some general overview of what I've seen in the industry. Again, I've only been in for 5 years and I've only been at one company. So there's a lot of caveats, as I'll mention in the next slide. Obviously, this brief just reflects my personal opinions, not of my company. It's a very coarse overview. It's not meant to be comprehensive at all. And it's and I'm inherently biased. So I like what I do. And I like the FFRDC role. So we'll just keep that in mind. So we'll go from there. The customer, right? So generally this is basically, where the money comes from in this world, right? The government, right? And what we call the customer. And so it includes a lot of different, Department of Defense is one of them, Department of Energy, NASA, NOAA, and they're basically they hold the power to make decisions on funding and proposal winners. So just gives you an idea of players, and in the end, we're all working for the government, whether it's a contractor, an FFRDC, in these roles. So that gives you just an idea of like, they're eventually the ones that have to make the decisions. And so if it's the DoD, you're generally working with someone that's enlisted in the Air Force or some other branch. If it's Department of Energy, it could be a civil servant of some sort. But in the end, they're the ones that make the ultimate decisions, and we are, we sort of work for them in basically any role, unless of course you become a government civilian. So I'll talk just briefly about contractors. So you've probably heard of these, right? So Lockheed Martin, Ball Aerospace, Northrop. They can be very large companies like those. So those, tens of thousands of employees, or they can be small companies. So a lot of companies, especially in outside of Northern Virginia, they're tens of employees and they rely on only a couple contracts to do stuff for the government. And so those can be very small technical roles, and you can get, involved with some of those companies as well. So don't limit yourself to just the big ones. They are profit motivated, right? So they are always looking to push out their market share, right? So they're you're always looking to make money, and in that case, you're always trying to win proposals and deliver things on time to get bonuses and things like that. So it can be a bit of a hectic environment in some of those companies. And of course, they live and die by the contract, right? They are contractors, and they basically are constantly proposing. So it doesn't matter if you have a good thing now. What about next year? And you're basically always trying to get work in. You're competing against the other ones for these contracts, and so it can be a bit hectic in that sense at these companies. They do, however, build hardware, right? So they are world-renowned institutions that can build amazing things like JWST. So there's only a few companies in the entire world that could have pulled that off, and these three all had their own part, right? So you can build some really, really cool things there that many other places can't. And the roles, and I'll talk a little bit more about this later, they generally focus on one mission. Given they're a contractor, right, you're generally hired for a specific contract given. So say, as my example, when I talk about weather satellites, so say they get a weather satellite and it has a spectrometer on it or something, they're going to need a spectrometer expert on that program, and you'll generally be hired for it. So it can be a bit harder to get into some of these companies, just because if you're not exactly the right fit, they might find someone else or something. So I'll talk a little bit more about that. So FFRDCs, these are federally funded research development centers. You've probably heard of some of these. Sandia is one, MIT, Aerospace, my company, is one. The national labs sort of operate like this too. The general sense is that they're nonprofits, right? So they're not profit motivated. And they basically act as the technical arm to the government. So basically when something happens or the government needs a good opinion that is non-biased on a specific technical issue, say like, the mirror was dropped on a telescope or something, and the contractor says, oh, it's fine. The government is going to want an independent analysis of that to determine whether it is fine or not and to make a decision on what to do next. And so that's where we come in from Aerospace or Sandia or MIT, Lincoln Labs, or other institutions across the United States. They're generally more of an academic environment, so they tend to hire a lot of PhDs and masters because they want to show the government, hey, look how smart we are. We have all these experts. Please use us. Please give us, funding. Generally, they don't build giant things like JWST. They mostly focus on, small experimental types of things. So, like at Aerospace, we fly CubeSats, a bunch of them, and operate them to do technology demonstrations, things like that. So it's generally on a smaller scale, but we are involved heavily in those giant programs as an independent analysis, during the whole process. And I'll cover that a little bit in the weather satellite sort of example I talked about. And generally the roles at these can cover many programs and customers. So as I'll mention later, it's a good place to start in this world just because you can get a lot of experience on different types of missions, sort of figure out what you like to work on, what you don't, just because, we have many customers all across the government space, and you can sort of pick and choose and decide, what's good for you, what sort of modeling or lab work you want to do and things like that. So, yeah, that's sort of again, a very coarse overview of those three sort of roles. So a case study, right? So this is just sort of a background of I'm trying to basically figure out, how does the government procure a successful weather satellite? So what goes into that? Who are the players in it? And what are their roles? And so in general, so you have an image on the left of GOES-T, which is one of the ones that I think was just launched. Lockheed built it. So, when the government is faced with this type of question, they need to do some background research, right, to determine, okay, what's the current technology out there, right? Like, what are we flying now? What are its pitfalls? And so that's where the subject matter experts at FFRDCs or in government come in and basically help them to say, okay, this is what you should be aiming for in the next weather satellite. So looking at what's being built now, what are the optimal orbits for certain applications, right? Like all these types of questions come into before we even start the proposal process of what do we need to do next and how can we go about it with the current technology that's out there, with the current, types of orbits, the type of launch vehicles in terms of how many can we launch at once. All these questions come in just at the beginning. And that's where the FFRDCs and the government sort of work together to determine, what technology is out there and who's best suited to build it. Step two is going to be actually writing the proposal. And so this is where the government and again, the FFRDCs come in and carefully craft a proposal and basically determine, what they want to apply to. And that needs to, basically come up with requirements like satellite will need to detect specific weather features, it has to view every part of the states every 60 minutes, things that technical goals that the contractor will have to meet in order to get to have a successful mission in the eyes of the government. And then basically once that proposal calls out, right, then the contractors on the other side come together and say, okay, how can we apply to this? What's the budget? Can we meet all the requirements listed? What can't we? What can't we? What modeling do we need to do, in the proposal itself to figure out, if we can meet these requirements and make a strong proposal, things that you obviously are, people who have written proposals in astronomy are very aware of, same techniques, right? And then of course, budgeting, right? Like, can we build it? Do we have the expertise? How much hiring are we going to need to do? All of those questions. And so the next few steps, right? So once the government FRCs get the proposals, it's, is the contractor analysis correct? And so that's where the independent technical analysis comes from. The FFRDCs use their in-house modeling tools to make sure that things are actually going to work. Can they meet all the requirements in the proposal? And then of course, as an FFRDC, you just provide an opinion and ultimately the government's going to make a decision. And then, 5 basically being the selection is made and the contractor begins building. And so this is where the real fun starts, right? Is deadlines come up, can the contractors meet them? If there's an unforeseen complication that arises, during the mission, which happens all the time, right? Say you have a detector that's has higher read noise than you thought at the beginning. Okay, well then the contractor is going to do their own modeling analysis to say yes, it can meet the requirement. FFRDCs will do their own and make their own independent opinion. The government will decide, and so it's just a constant back and forth throughout the whole life cycle of the mission. The FFRDC is basically always there as the technical arm of the government, and then of course the contractor is always pushing forward to meet their deadlines and build the satellite. And then launch and ops, right? And so we have launch vehicle certification, which is a group FFRDCs generally do, but the big thing, right, is data dissemination. And so this is where a lot of the data science, machine learning stuff comes in, and this is a huge growing area in all of aerospace, right? Where's the data going to go, and what's the best way to exploit it? And so, a lot of these smaller missions don't have as big of data pipes down to the ground, and so they can't provide raw data. Well, can we do some onboard processing to just send down small messages instead? And so that's where the sort of data science, data algorithm processing comes into account. How is it calibrated, right? Things that astronomers are very good at with a flat field, all those types of things that you've done. Those need to be done on these need to be done on these missions as well. And then again, how is it exploited? So some of the fun stuff is what I recently saw was, for weather satellites is NOAA wants to know, okay, we built this to track hurricanes, but what can we do with forest fires, right? How can we actually use this data and exploit it correctly to provide information to firefighters on the ground? And so it comes into basically all new types of data reduction techniques, maybe some machine learning to determine what images to look at first. So that's a big growing field in this area, as well as everything that's being done in tech, is being done in aerospace. Okay, so where do you fit in? So in general, and these are just very coarse things, don't take these as gospel. Most positions do need a US citizenship. That's just the nature of the work. It's basically almost a given in this industry. In terms of holding a clearance, it is preferred, and I say that because it can open up more doors, just because there is a lot of work, in the cleared environment. But again, there's a lot of commercial work going on right now. NOAA, NASA, all these companies or all these organizations, need help as well, and those are all done in the unclass environment. But you can open doors and make it easier to find work if that's something you're interested in. And these last two bullets are basically just some very cursory things I've noticed when I was applying. Again, don't take them as gospel, but in general, contractors tend to employ for specific roles. So as I mentioned before, it can be difficult to find a good fit, especially when you're starting out. Just because if you're not exactly what they're looking for a specific contract, it can be hard to get in. FFRDCs are again, a more academic environment and are more willing to employ, just highly educated people to train. So yeah, it's a better place to start, at least what I found, especially if you're looking to switch, like not do what you've been doing. So like I was an X-ray astronomer and I don't do that at all now. And aerospace was okay with that. And I feel like FFRDCs are more okay with just hiring smart people that they can train and find, where the work is at the current time when you get hired. You can start doing that and adjust if necessary. So you can sort of learn on your feet. So yeah, this is sort of the end slide here. Again, this whole industry is vastly growing. Again, there's a lot of more commercial vendors in this field now. The access to launch is a lot cheaper, so there's a lot more launches per year. Yeah, it needs smart people like all of you in the room. So many opportunities, employers, and then again, you can still sort of use your physics background, right? And you can still touch cool things, do hardware if you want, do a lot of physics-based modeling, which is a lot of what I do, and have a great career in this field and work on really, really cool stuff. I mean, I'm constantly turning down work because I don't have time, but it's all really cool, interesting things to work on. So yeah, And I guess to end, I'll throw up this again. So yeah, feel free to email me directly at the red address below. My company's hiring. I believe basically every aerospace place is looking for technical talent at the moment. So yeah, with that, I'll stop and take questions.
Questions for Chris?
It's maybe don't know a whole lot more about this, but I was wondering if you could talk a little bit more about how security clearances work. But I have like a few friends who like served in the military, and when they got out, they had one, and it was like the thing that like allowed them to break into like whatever industry they wanted to work in. So I was curious how that works for like, people like us who been in school for a long time.
Yeah, I think I got most of that. It was mostly about security clearances. So yeah, generally, a lot of the positions you'll apply to in this realm, they'll say in the job app, security clearance preferred. And you can obviously reach out to them and ask exactly which one, because there are many different levels and some are no big deal, some take longer. But yeah, it's not that bad. It's just it's something that once you have it, again, it's good and it helps grow your career and offers a lot of work. But yeah, again, it's not necessary, as I said before. But yeah, I'm happy to talk more offline about specifics if you have something in mind. But yeah, in general, the employer will work with you to do all the background and all that, and you'll get a sponsor. So it's nothing that you really have to do. It's just something that you have to submit yourself, I guess.
Other questions? All right.
Hi, any tips on how to make that transition from the key man to aerospace at mid-late career level?
Yeah, I mean, in that sense, we hire mid-career people all the time, at least at my company. And if you have a specific something that you think applies to this, or you want to completely change, directions in terms of your experience, I think that's okay as well. Yeah, I would look, again, I would, just in my opinion, right, I would focus a little more on sort of the FFRDC national lab side to really, because they're more interested in just hiring very experienced people. But yeah, we hire mid-level career people all the time, and they're very successful. So I wouldn't be worried at all.
I see a question online. Can you talk more about modeling work you do and how it compares to programming experience from graduate school?
Good question. Yeah, so I do a lot of like space domain awareness modeling. So basically, keeping track of space traffic management kind of stuff. So in that sense, you're using sensors and things that I used in grad school. But it's a lot of stuff that I didn't work on, right? Like orbits and orbit determination and figuring out where things are going to be in the future. So it's nice to have a good base, right? And I'll say too, like it's all in C++, which I had zero experience before I started at Aerospace. So don't let like that deter you from if you don't know a programming language, you'll learn it. So yeah, I would say that it's nice to have a good base of like a Python or object-oriented programming and things like that, and a good physics background. But you'll learn a lot on the job in terms of the specifics and all the physics and things like that you'll need on at your position.
We should move on. So let's thank Chris again.
Thanks.
Okay, I'm gonna quickly share the presentation so I can present. Where did it go? This thing hates me, I swear. I don't know why I lost the screen. Is it presenting there?
I see a screenshot of the schedule.
Really, why? Why on earth? Okay, let me. Can I? It moves this thing too much. I'm horrible at this. Okay, I'll try again. Here it is. They all have the same colors. There you go. So our next speaker is James Guillochon. I hope I'm not butchering your name too much.
Perfect.
James is a data scientist with a diverse background in astrophysics, robotics, and computational fluid dynamics. He holds a PhD in astrophysics from the University of California, Santa Cruz, and completed a postdoctoral fellowship at Harvard. James worked at an industrial robotics startup and is currently a data scientist at a leading GIS company. Go ahead, James.
Thank you very much. Let me share my screen. Yeah, that works. All right, can you guys see that? Nope. Yes, the Zoom share, there we go.
Yes, looks good.
Okay. Yeah, so my name is James Guillochon. I am giving a talk today basically on the breadth of things you can do as a former astronomer. So let's just get right into it. Here we go. So I'll just go briefly into who I am, how I got my jobs, my last job and what I did there, my current job and what I do there, and some basic job hunting advice. So who I am, I'm originally from San Diego. I went to college at UC Irvine, got a bachelor's degree in physics. My senior thesis advisor was James Bullock. It was dwarf galaxy disruptions. Betsy Barton was actually one of my professors when I was at UC Irvine as an undergrad. I don't know if Betsy's still there in the room, but yeah, I always remember her complex analysis class as being one of my favorites. And Betsy, if you're there, Jorge and Omar and myself still regularly communicate with one another. So you know that was fun. We all really enjoyed that class, and yeah, I say that in all sincerity. It was one of my favorites at Irvine. After that, I got a job at a company called HRL Laboratories, which is in Malibu, and they are kind of like Bell Labs. They work on a wide variety of things. I worked on unmanned aerial vehicle command and control. This is way before drones were kind of a mainstream thing. I think a lot of the things that I was working on now can be found in like $50 drones that you can buy from Walmart quite easily. But I was there for 2 years, decided I wanted to do something to further my education and go into something interesting. So I went into astronomy. I went to UC Santa Cruz for grad school. Got a PhD there in 2013. Enrico Ramirez-Ruiz is my advisor. And then I did a postdoc at Harvard for 5 years, and Avi Loeb was primarily my advisor, although I worked with others there, as you do as a postdoc. So my academic summary, my PhD was on the tidal disruptions of stars, supernovae for merging white dwarfs, and hot Jupiters. I used a code called Flash to do that, so it's primarily massively parallel hydrodynamical simulations that I worked on. I got a little bit bored of that. I also saw it as not being a great career stepping stone if I wanted to go into industry, working on these large fluid simulations. It just didn't seem like there were that many jobs out there. Data science is kind of this up and coming thing in the mid 2010s. And I thought, well, I should broaden my horizons, make myself a little bit more palatable to industry, should I go in that direction. So I pivoted in my postdoc to doing more analysis of observations, data catalogs, light curve fitting, and a couple of oddball things with Avi, like SETI, some stellar dynamics stuff, and was just trying to broaden my horizons, I guess, and also just make myself look a little bit more useful to people in industry. While I was a PhD and a postdoc, I ran Boxcarta, which was a recommendation system for papers on AstroPH. I stopped running it about 2 years ago. At some point, it was just too much for me to continue to maintain. It was running very ancient software, but I do believe it had a relatively good impact in the field. Lots of institutions used it to host discussions. I also created this thing called the Open Supernova Catalog, which is still running, although admittedly the front end has died, and now it's just the API. Talking with some people in the field to see if there's going to be a 2.0, but it won't be something that I run. It just kind of will migrate to that eventually, maybe. And the only other thing that I really am active in still is I maintain this spreadsheet of physics GRE policies across astronomy programs, keep track of where it's optional or required and things like that. I'm hoping, based on trends I've seen, that exam will not be used at very many schools at all soon, and I can stop maintaining that too. So then that would be a mission accomplished. In the end, I just pulled up my name on ATDS today, something like 7,000 citations in total, 20 first author publications on 100 pubs in total, refereed a lot of papers. I applied 4 times to faculty jobs, roughly 50 positions. I got 5 shortlists, but no offers. And it was just the way the cookie crumbled. Every single time I was on a shortlist and I met all the other candidates for the position, I'm like, wow, you guys are all great. You all deserve faculty positions. I saw like the various strengths of all the other candidates, and I said to myself, well, these people are all great. They should all get this job. But it's brutal. And my understanding is that it's gotten even more brutal since I last applied in 2018. And at some point, enough was enough. And I said, I'm not going to do this anymore. I was putting my family through a lot of stress, myself through a lot of stress. And I decided to make the leap to industry. So, the industry, those numbers I rattled off there are pretty meaningless. Honestly, the things that mattered the most were what my PhD field was. People hear you're an astronomer, an astrophysicist. That's just a nice talking point. Lots of people like those sciences, even if they never got into it seriously. The Harvard name mattered a lot, unfortunately, just because it's a famous college. And I also had a brief appearance on Nova, and some people actually had seen that, and that helped too. So, these are silly little things that honestly in the academic community are pretty meaningless, but had an outsized importance when I was applying to industry jobs, which I found, surprising, but on retrospect, it kind of makes sense. So before I got my first job out of academia, I went through one of these data science boot camps, the Insight program. The way I got into that was that I contacted Taka, who was one of the speakers today. He had done the Insight data science program earlier. He referred me into a program. I got accepted. I also did a little bit of job hunting on my own on the side before I went through the program. That was a failure. I did really poorly in the interview process. I just didn't have the common sense knowledge of like what you're supposed to do in an interview to come off as being very attractive as a job candidate, I think. I went through the program Insight in 2018. That also was a failure. They only placed about a third of us in jobs. It was clear to me at the time that the program was going through some issues. That was later validated for me when another friend of mine went through the program a year later. Same issues. Insight went out of business temporarily in 2020. They're back in business now under a new model. I haven't really looked at it in great detail. So I don't want to dump on them too much. They might have fixed everything that was wrong with them back in the late 2010s. But at the time, it was something that, it just seemed like it worked well in the mid 2010s, but things evolved so rapidly that by the late 2010s, their particular approach for placing people wasn't as effective. So how did I get my jobs? My first job at Berkshire Grey, the industrial warehouse robotics company, a postdoc friend of mine at Harvard, his roommate was hiring engineers. So I basically talked to that guy. He got me my foot in the door, got me a few interviews. Eventually I got hired. At Esri, my second company, another postdoc friend's sister-in-law's friend's company, not kidding, was hiring data scientists. I talked to that person on the phone maybe 6 months before officially applying to a job, just as like kind of a get to know him kind of conversation. I honestly wasn't looking for a job at that time. It was just I thought nice to make a connection with someone. And you know, I think in both of those cases, my specific background as an astrophysicist, this famous institution, was a good talking point and impress people. And I needed to actually talk to people to get far in the interview process. Most of the cold resume submissions I had were completely ignored. Very
James?
Frustrating. Yes.
I will interrupt because people pointed out indeed that the slides are not changing, at least for us in Zoom. Are they meant to be changing?
Yes, they're supposed to be changing. Oh, Jesus.
Oh my God. Yeah, so we've been missing them, but I don't know why.
Okay, one sec. Da-da-da. Your screen
So
sharing.
now we do see it.
Okay.
You are screen sharing, yeah. But it was just not moving through the slides. So I guess if you go to the one where you were before.
Interesting. So when I hit play in Keynote, it pauses the screen share. I see. 1 second.
Well, you can just leave it like that and move by hand if you want.
Let me try and share the whole desktop instead of just my.
Okay.
Sorry, guys. Can you guys see the slides changing now? Okay.
Yes.
So I had nothing on these slides except for words. So it's okay. I think that you didn't actually see them. Let me just skip through where I was. Now you can actually see the funny image I made to go along with how I got my job slide. Anyway, yeah, I think referrals are incredibly important for getting your foot in the door. They help so much, and don't be shy about taking advantage of even tenuous connections you have to people that might get your foot in the door for an interview process. I have no shame about this at this point. I did kind of originally when I was, first looking for a job, but it's something I got over relatively quickly. And I think it's just great to talk to people. And I see now I'm being partially blocked here with a screen share. There we go. Ta-da. Okay. And I don't know how to hide this. Maybe if I do this, there we go. All right, mostly unblocked. Okay, first company I got a job at was Berkshire Grey. It's an industrial warehouse robotics company. They basically automated a lot of the stuff that's done in industrial warehouses when it comes to fulfilling orders, for big players like Walmart and Target. And it was interesting to see that, Betsy was working for Walmart roughly when I was at Berkshire Grey, at least the second half of the time I was there. We are actively deploying a solution in one of Walmart's distribution centers up in Wisconsin during that time. So it's a bunch of integrated mechanical pieces of equipment. There's a robotic picking arm that picks items, as you can see in the video here, and places them in other locations. And this is actually done by humans a lot of the time in these facilities. And so the idea is to automate away some of that and get rid of that kind of backbreaking job. So this was I think a really fun job. It was really out of my comfort zone. I was doing a lot of stuff with hardware and software. Had a great team. We, built stuff in a small little warehouse outside of Boston as a prototype, and then deployed it at a customer site. A lot of fun. Did that for 2 years. And I was primarily, I'd say, a software engineer at that time. I was a generalist. People were aware that I had a fairly broad background. And data sciencey things were maybe 20% of my job. I did some data science stuff. Most of it was software engineering for command and control of these automated systems. So that was really a lot of fun. I enjoyed it a lot. And here's an example thing I did when I was there. Basically, we had this issue where the robotic arm was picking items more than one at a time on accident. And this is just because the camera wouldn't necessarily locate where the items were very carefully. So I had to come up with an algorithm that would very quickly decide whether the robotic arm was holding on to one item or two. in the middle of the pick. And so I had to do this in less than a second. And my solution was actually a maximum likelihood comparison between a single and a multi-pick. And this is actually using the exact same code I had written to fit transient light curves back in the day when I was doing that as a postdoc at Harvard. So it's a nice bit of continuity that I was able to leverage at this company. So that was nice to have at least some level of continuity. Okay, so I eventually started working for another company, Esri. And let me just first describe what Esri is, and I'll tell you why I switched in a moment. So Esri is a geographic information services company founded in 1969. They're probably one of the oldest tech companies that are in existence. When they first got founded, they weren't using computers. They were using paper maps to help out government customers. They started using computers maybe like a decade or 15 years after their creation. Put simply, what they make is a massive collection of tools for dealing with maps for government and commercial purposes. You can think of them as like Google Maps on steroids for business and government. There's 5,000 employees based in Redlands, California. I'm fully remote from San Diego. They're a private company, so they have profit sharing, but no equity. So, you know, startups and a lot of things in tech tend to have these pretty equity intensive payment for their employees. It's very different at this company. It doesn't have a tech startup feeling at all. It's old. There's been people who have literally been there for 45 plus years. And so it's kind of a different environment than your tech company might be. I'm an internal consultant. I'm a senior data scientist. And my job, I'd say, is like 70% data science. Sometimes I'm doing data engineering type tasks or ML ops, or even just giving presentations and talking to people, giving them suggestions of what they might do to solve a problem. But I'm mostly doing data science now. So one interesting thing that Betsy brought up in her talk was, you know, she misses AAS because it's a nice large community. You get to see all these people. So Esri themselves has this thing called the user conference. They hold every year at the San Diego Convention Center. Last year, there were 15,000 attendees. That's comparable to AAS. And it is kind of a bit like a GIS party. It felt very much like AAS did to me when I went to AAS meetings in person. And there are conferences like this that you can still attend regularly in many different fields and industry, should you go that direction, where you can kind of get that sense of community. It's not exactly the same as AAS. I'd say it's a little bit more tight-knit in astronomy than it is in something like this, but there are these kinds of things you can attend. All right, so why did I change jobs? BG was a startup in the process of going public. It was getting pretty intense towards the end. The balance is a little bit too much in the engineering side for my comfort. I was doing data sciencey things at first when I got there, and then it got a little bit more mechanical and let's just deploy, you know, the solution for the next customer kind of work towards the end. And you know, most importantly, it was not in Southern California where most of my extended family is, or my wife's extended family. Our daycares kept closing due to COVID over and over and over again. So I was, you know, doing childcare quite frequently, never able to, you know, have the kids like conveniently go to grandma's house or something for a day when childcare was closing down. So I basically targeted jobs in the Southern California area. I happened to utilize the connection I mentioned earlier to land something at Esri. And when I did the interview with them, I really liked the company, and particularly the group that I'd be working with. I found out that I would work with a wide range of customers, work on a wide variety of problems. And the team was essentially a bunch of PhD recipients from many different fields. That seemed like they'd be fun to talk to. So my colleagues at Esri that I interact with on a regular basis are, you know, a former economics professor, a former ecologist, a volcanologist, a geologist, aerospace engineer, and also a good mix of younger folks who've just got their bachelor's degrees in a variety of things. And so it just seemed fun, right, to talk to all these people who understood different things than I did at a level of depth comparable to the level of depth that I feel like I understand astronomy and astrophysics. So it just seemed like kind of a fun environment to be in. My day-to-day at Esri is I primarily use a piece of software called ArcGIS Pro that they make for Windows desktop. It's basically a software suite that houses hundreds and hundreds of individual tools that do specialized things for the different customers that use it. As a consultant, I'm typically helping customers create workflows that do various things that are kind of in the data science category of stuff. It's a lot of image processing, classification, segmentation, but some text analysis as well. Oftentimes I'm just combining off-the-shelf tools within Pro or our enterprise software to deliver a functioning pipeline to a customer. And other times I'm doing bespoke solutions where I'm writing custom code to fill in gaps where, you know, our core software doesn't quite fit the bill just yet. The engagements with customers are quite varied. They can be very short, only a few hours. That may be more like a consulting workshop type situation where I'm just helping them figure out what to do, to several hundred hours where we're trying to deliver a real working solution that they'll deploy and use for some time. So just to give you an idea of like all the different things I've worked on at Esri, and this is to, you know, varying depths of sophistication. I've done a project where we predicted where rogue waves might occur in the ocean in the future. That was with the Naval Research Lab, which I think Christopher mentioned he was working at a couple years ago. Extracting dirt roads from satellite imagery, that was for a car company looking to basically add a feature for their off-road vehicles to navigate for them. Classifying ice from radar and satellite imagery near the Earth's poles, that's for NOAA, NRL collaboration. Determining a location of things along a rail line from LiDAR imagery. So this is 3D point clouds. Geolocating water meters, which is a pretty mundane task for a US city's water utility. Extracting easement boundaries from scanned property descriptions, very similar to what Taka had described, though at a much more POC level, as you'll see. Forecasting where algae blooms are likely to occur in the next few days. Classifying satellite imagery into land types, and determining the effectiveness of road barriers and reducing the incidence of fatal crashes. So all over the place, right? Like these things are very different customers, very different asks, very different methods for all of these things. And for me, as a person who gets easily bored, this was a pretty good match for me. So I just wanted to, I put this slide together after Taka mentioned what his company was doing, just because I want to show something I was doing that was relatively similar, but at a level of depth that's much, much less sophisticated than what Taka had done. These easement descriptions were basically taking these textual descriptions of where things are in a particular property and converting those into features that appear on a map. And I used, yes, someone talking? Nope, okay. This is done using Tesseract to do the OCR, which I think Taka had on one of his slides. And you know, I only had tens of hours to work on this. So rather than using something sophisticated in ML, I'm using a lot of regex to figure out how to draw these shapes. This is a little bit more appropriate here because it's a repeating pattern. These documents all look pretty similar to one another. Okay, so last slide. I think these are just kind of a good loose set of rules to consider when you're applying for a job. Many of these are touched upon in the prior Q&A and other people's talks. But you know, I think it's important to have a good resume that highlights your skills, your problems you've solved, and most importantly, your ability to work in a team. I think people are looking for that. Programming, I think you just need to show, as Christopher mentioned, competence in mainstream language. So Python and C++ are two of those. But some of the more boutique or old languages that we might sometimes use, like Fortran or IDL or something like Rust or Julia, which is up and coming, and those are not quite as palatable to people. So it's good to have like a base of knowledge in one of the mainstream ones. Data science, I think you already know how to do science if you're attending this talk. Vocabulary is one of the things you just need to work on. I think taking Andrew Ng's course online could really help with a lot of that. Although I think it's less and less necessary nowadays, because I think even astronomers are getting very exposed to this terminology in the line of their own work. I think, big thing in interviews that helps people decide whether to hire you or not is how well you can talk and communicate. So the stories you tell about how you interacted with others and solve problems, I think, carry a lot of weight and can convince people to hire you. And lastly, I think you should just spend a lot of time networking, making connections with various people, because you never know where those connections might lead. And for me, I'm interested in making connections just for fun. It's interesting to talk to people who come from different technical backgrounds and just learn about what they do. And I think that's one of the key perks of the job that I have and the academic environment you guys all come from. So that's it. I'll just leave this up and take questions. I'm sorry about the screen sharing issue.
For James in the room.
Hi, James. Thanks for your talk. Between your time at BG and Esri, or at least the roles that you had at those two companies, they may sound quite different. So, was there a lot of overhead or something like to get yourself up to speed to work at Esri? Did you have to acquire new skills in that transition?
So I think for the first job at BG, the answer to that is yes. I did have to, it took me 3 to 6 months, I think, to get comfortable in that job. It was really different and out of my comfort zone. Esri is a little bit more close to an academic environment. As I said, my group was a bunch of PhDs. And when I did my interview, I was talking to people who had PhDs, and a little bit easier to just kind of talk to those people than it was to talk to engineers as I had to at BG. So yeah, I think it was a little bit more natural to fall into a data science role at Esri than it was to fall into the engineering role at BG.
Question from Zoom. Did you learn about GIS before applying to Esri or kind of on the job?
A little bit. I learned about GIS before I applied to Esri. I mean, you have to do your homework. There's no way you can do enough homework to be impressive in what you know if you're coming fresh to a new field. You just need to show, I think, interest and the willingness to learn. And that can be done by, taking, reading articles and maybe taking a few random courses, informal ones, and just getting to know the lingo a little bit. But it's really interest, right? Like, and not that you're just going to come in and they're going to have to teach you everything. Like, you have to show to people that you'll take the initiative and learn quickly when you're on the job, get up to speed, and be a contributing participant relatively soon.
One quick one from Zoom. Does Esri require US citizenship?
It does not. As Christopher had said, there are some customers that require clearance to work with. Clearance, I believe, requires citizenship most of the time. Esri does a lot of work for non-cleared stuff, for water departments or state governments, local governments. They have something like 1,000 active contracts with different kinds of entities. There is a good amount that is, behind the fence, cleared work for the DoD and other, military agencies and stuff. You don't have to do work for those for that part of the business if you don't want to. I've found so far a lot of freedom to choose what kinds of projects I want to work on. Yeah, hope that answers the question.
All right, so next up, we're going to take a little bit of time for our next sort of group discussion, panel discussion. We've got a few of our speakers still on the Zoom webinar, a couple folks in the room. And so we decided to kind of talk about, since we had, I would say this is the broadest type of jobs that we've ever had at ATDS. We have people from a wide range of industries, not just sort of classic data science and engineering, but stuff from aerospace engineering, robotics, social media, lots of different stuff. And so we thought we'd kind of open it up and chat about what falls under the data science umbrella. ATDS is a nice acronym that I like, but as a couple of people have pointed out to me, it should really be astronomers turned data people, or data adjacent people is another term that I think James and I have used in the past. So yeah, folks on Zoom, especially I think James and Chris, do you guys want to give a little bit more insight into what you feel falls under this umbrella and what folks in the room are good at doing?
Yeah, I can start, I guess, as Chris. Yeah, so data science is a weird word, right? It's something, I don't know what the history of it is, but it's stuck. And it's a wide world in terms of a lot of industries are using it to basically, there's a lot of data in a lot of industries, be it aerospace or in robotics, and everyone's trying to utilize that. I think, what astronomy provides, right, is a very, it teaches you how to be a scientist more than anything. And that's something that no matter what field you're in is gonna certainly pay dividends, right? And that's what a lot of these companies are looking for. And so, there's these schools that I know Jeff has done in the past to do these data science sort of types of things that help you learn these specific Python tools and things like that. But in another sense, there's just a need for science and scientists across a lot of these industries. And you don't necessarily need those exact skills to get these types of jobs, at least in the aerospace world. Yeah, I'll let other people talk.
Yeah, I mean, there's been I think the expression is a title dilution, right, with data science. And we had an interesting talk the last time I went to ATDS in 2020 by, I forget who, but someone who worked at a job website that, basically looked at what's the average degree of people going into data science. Is it a master's, a bachelor's, PhD? And it's trended towards, lower degrees over time. And it really spans the gamut now. You can be called a data scientist as someone with a bachelor's degree, or even not even that in some cases, all the way to someone who has extensive experience. And there's lots of prefixes: senior principal, data science lead. All these things further muddy the waters as to like what your actual day-to-day job is. I think we'll see where it goes. As Christopher said, the title has stuck, but I think people shouldn't pigeonhole themselves, right? Like, you shouldn't be like, okay, I'm going to become a data scientist, quote unquote, and therefore I'm not going to look at any job that says engineer. Google calls all of their data scientists engineers, even if they are technically data scientists, except for people who work for Google Brain. But within Google's main company, they're all engineers. And I just think you shouldn't limit yourself to what you consider. If a job looks like a good fit for you in terms of matching your skills, it seems fun for you to try it out, you think you'll do well at it, I say consider it seriously. And the title shouldn't be a barrier.
Yeah, just talking about titles for a second, data engineer, Stephen in the chat mentioned this, and I do know some people who built or have worked on in astronomy large data reduction pipelines. and, you know, pulling in data, moving it around, doing something to it, and then placing it somewhere else. That's a data pipeline. That's what data engineers on my team do. And sure, they also know sciencey type stuff and machine learning type stuff, but if that's sort of more of your expertise, or people from astronomy with that expertise, then data engineer or potentially machine learning engineer, if you're doing more of the modeling side, those are also titles that you see in these kinds of roles. Questions from the crowd around this? Yeah, please come up to the mic if you can, if you're able. Thank you.
Right, so a quick question here. So data science is evolving, every day. If you want to go with the fancy stuff like a CNN, some time series, or some NLP techniques, you can actually get into a rabbit hole on all the different new, up and coming techniques that you want to learn. But as someone who's starting out, what are the indispensable skills that someone who's trying to get into data science should have? And is it a good idea to like get a little bit of taste of all the different techniques, or maybe just focus on some and then pick up things as you get into a job and if it needs it? Yeah, thank you.
I'll repeat the question just to make sure we hear it on Zoom. But the question, and hopefully I can capture this accurately, is sort of, breadth versus depth of data science topics, machine learning, right? Should you try to learn a little bit about many, many different topics to get into the field, or should you try to become maybe more of an expert in a small number? Excuse me. I'll give my 2 cents real quick as someone who's hired a lot of data scientists and engineers over the years. I think it's very important to know the very, very top level, like kind of terminology of a bunch of stuff. You should know what CNN versus NLP stands for and kind of what they're used for. But if you've never used them in any sense, that's fine. But you probably should know a couple of things a little bit deeper. One of the classic interview questions is, what is your favorite machine learning algorithm for data science roles? And then I'll dig deeper. Why did you pick it? Is it your favorite? What are the pros? What are the cons? If you say there are no cons, I'm probably not hiring you because nothing's perfect. Other folks on breadth versus depth and fundamental kind of data science, machine learning skills that everybody should have going in.
I feel like data cleanup and visualization is absolutely paramount and critical to your day-to-day job. And just being able, like if someone hands you a CSV file of records and it's got misspellings and, issues with it that you have to clean up and fix, it's good to know what tools to use to clean that up and visualize and get it nice and clean before you throw any ML tool at it. And I think that's one of those things where regardless of what you're doing, whatever fancy algorithm you're throwing on top of that, that has to be done first. And I know it's tempting to like use the latest and greatest fun AI thing that does something really cool. But if your data is garbage, it will do garbage things and you won't understand why. So I really think like the data pre-processing and cleanup tools are absolutely essential to learn if you're going to go into the field.
And can I add one more? There's something that we all practically know, that anybody that has handled a table knows how to do relational databases, bigger or smaller, but that's something that is used in so many of the positions, almost regardless of what you do. You will have to do relational databases. Most people use some version of SQL for that. But my point is, all of us have used similar tools, whether it's SQL or something else. During our research, we use that type of thing. So that's something that you know already, just figure out the terminology around that, because in most interviews, it will come up. And some people may even ask you specific things about it. But that's a very basic thing that is just getting the right language around it. I mean, you already know it.
Yeah, Uma.
Yeah, I just wanted to add one thing there. I think plus one to both you, Jen, and what you said about breadth versus depth. I would say that another thing that you should have is fundamental statistics, and you should know distributions. You should know when what can be applied, and apart from that, you should know something in depth. And this can be what you did for your thesis, and if you can translate that into something relevant to the organization that you're working in. Like, hey, I did this for this reason, but it translates very well to something that you care about, that means. So, and like Jeff said, when I interview, I look for breadth as well as depth. And that depth doesn't need to be what I'm specifically looking for, but I'm looking to know whether you have been asking the right questions to go deep. What did you balance? What, if you chose a particular method, what did you discard and why did you discard? Because that's what we want you to be able to do, is balance different things that you know and figure out what is the right solution and why do I pick this solution or something.
Yeah, I think that was something also that James was bringing up, and maybe even Chris as well. But you know, telling a good story, not only of your background and why you want to work at this company, but a good story of a project you did, and yeah, the details and decisions that went into everything. Hopefully, you have a better story than my advisor gave me data and said write this paper, and if you don't, come up with a better story, right? Yeah, Randolph, I think there was a question or comment.
A question actually. To kind of, as was my mention, one should learn kind of things, kind of know the knowledge, language. What about certificates? Does it help to get a certificate from, I don't know, Coursera or competitors to show to show that you kind of know actually machine learning, or does it sufficiently to kind of do some short courses or YouTube videos to just know the lingo?
Yeah, great question. I'll just repeat it real quick. How much stock, for all the data folks and especially people who have hiring managers, how much stock do you put in certificates from online courses or short courses versus just I took this class versus not even mentioning that in a resume or interview? Julia's got her
I'll
hand
give
up.
an initial answer to this. So at my job right before this, where I work now, I was a data scientist at Stack Overflow. And Stack Overflow has, at the time, had like the main way Stack Overflow made money was through a jobs board. That was the main like source of revenue. And so we had a ton of resumes, like we had data on tech resumes that people had submitted, and then jobs, and then we knew whether they had gotten an interview, and we had some data on whether people got hired or not. And so we could like, I actually did train a model to say what on people's resumes was impactful for getting interviews and eventually getting hired. And of course, like if you have more experience, if you've had more jobs already, like these are the things, you know, very obvious, right? But like, what are people more likely to be looking for? Education, increase people's likelihood, especially at the master's level. These, again, this is Stack Overflow. So this is not data science specific. This is tech in general, software engineering in general. So especially a master's degree really helps you get those interviews compared to not having the master's degree. We didn't see as much difference when we got to a PhD. So it turns out when it comes to certifications and certificates and all that kind of thing, they're basically worthless. Like they basically have no impact on whether you're going to get an interview or hired. I say this as someone who, if you were around when I gave my talk, I took like every MOOC that existed when I was like transitioning into data science, but I don't have any of those. I mean, certainly now I don't have any of those on my resume like 8 years later, but even at the time, I didn't put any of those on the resume. They were helpful for me for learning because I came into this without, you know, the vocabulary about what like things are machine learning. So I'm glad I did them, but I think we have evidence and probably a lot of personal experience that as hiring managers, that like that's not something that it's not a differentiator, you know, like basically everyone who's applying for these jobs have done these kinds of things, and it's not something to highlight on a resume.
I'll plus one that for whatever that's worth. I agree. I don't think they're that useful. I'd much rather you talk about what you learned in those courses rather than just, I got this certificate.
Yeah, I feel like if you're in the ops realm of things, I've known people who have gotten certificates, but it's kind of like when they already had the job, it was more just a way of furnishing their skills so that they could learn something else that they needed for their job. So it wasn't like used as a tool for getting a new job or anything like that. It was just more of a concrete quanta of knowledge that they acquired to help them do their jobs better.
All right, we have another question in the room.
Hello, so my question is, how would basically, how would everyone go about searching for jobs if, let's say, in my specific position, I would like to be tied to a certain geographical location, like let's say San Diego, for example. So kind of James, kind of resonated with me a little bit. Or at least, how would you go looking for remote jobs in that sense? Because it seems like there's a general consensus that you shouldn't kind of blanket send out a whole bunch of resumes, but at the same time, kind of look for either remote or hybrid or stick to one particular city, for example. Or any given strategies that would help out in trying to look for jobs in that specific area.
Jeff, would you mind kind of paraphrasing? I had a hard time hearing.
Yeah, of course. So the question was around specifically trying to search for and apply to jobs either in a geographic region, and San Diego was the specific request, or remote hybrid type roles. One thing that we were chatting earlier that I did mention was, sometimes, most of the time nowadays, the job description will say remote, fully remote available, hybrid with these cities or areas. But the details are still very fuzzy oftentimes. So usually, in my experience at least, you have to kind of wait to hear back from that place to get any kind of more info. Like, it's hybrid and we expect you to be in the office 3 times a week, and you have to report to any office that we have open in the world, not necessarily where your team's based. So like, there's all kinds of different combinations nowadays of that kind of stuff. Does anybody else have advice or thoughts on that who have gone through that?
I wanted to say one thing, because the company I was just working for is fully remote, like the entire company is remote. So I definitely had to do my entire work in front of a screen the whole time I was working there. And, originally I may not have, it was a pandemic and a bunch of people were remote anyway, but I get the feeling that there was a revolution. This company in particular was already remote, that they had zero issues with dealing with the pandemic for that reason. But I get the feeling now that the demand for having at least hybrid, if not fully remote, is so large. People just got used to living in their pajamas and being comfortable, essentially. So I think remote, I see a million positions that are advertised as remote. So you should totally just don't take it into account. The only thing is, if there's something that you really like and they specify that is in person, that's the only time when you may get into trouble. Otherwise, remote should always work as an option.
James, I think I saw your virtual hand up first.
Christopher was first, actually.
Oh, okay. Sorry, my bad.
Yeah, no worries. Yeah, I will say, across the aerospace enterprise before COVID, there was zero hybrid, and now basically every company is offering it. So that's always a good thing to see, especially in these companies that have been around for decades. But I will say another advice too is if you're looking to live in San Diego, figure out what industries are in that city and start, it's a big aerospace city, right? So look at the contractors, look at what kind of jobs they have. Go to career fairs, things like that in the community, and see where you could fit to make your life easier. And of course, there's always fully remote stuff, and there's much more of that now. But if you want to, it could be a good idea to just see what's in the city itself.
So yeah, I guess like San Diego's name dropped here. When I went to Esri originally, they had a satellite office in San Diego, small 30-person office. And so I was relocated when I got hired to San Diego. And I thought the expectation was that once COVID had kind of wound down, this is an older company, they've been around for a while. I was expecting them to kind of enforce back to office, at least hybrid. They did try, but basically no one wanted to go back into the office, particularly the small satellite office where much easier if everyone just was absentee at the same time. It's less noticeable, I guess. And they eventually closed the satellite office. So in October of last year, they shut it down. I'm fully remote now. I'll say that if you're going to be fully remote, it is a big plus to be in the same time zone as the company's primary activities. Some companies are spread out. They have like multiple offices, one in Europe, one in California or something, and then there's no natural time zone, but many of them, they're headquartered somewhere. And if you're not in the same time zone, it can be painful. Before I relocated, I was for a few months in Boston working for Esri. I was on the East Coast. There was meetings I had at 5 a.m. regularly. It was kind of painful. So that is something I would recommend, like no more than like one time zone different. Otherwise, things can get a little bit complicated, particularly if you have kids and other regularly scheduled things that can get in the way.
All right, we have another question in the room.
So I understand that data science is such a quickly changing field and it's so diverse with all the different types of jobs and different disciplines, but where do you see kind of the biggest change or where the field will be necessarily, like, the next 5 years, where you feel like, oh, I'm feeling that there's a sentiment of, this feeling towards our discipline, and it's something that we should keep in mind as we apply and think about ways in which we can improve our, just resumes and just being or thinking that data science. Thank you.
So to repeat and summarize, where do we see data science in 5 years, basically? But also, I think the more interesting part of the question is, where do we see the field going, and how can research astrophysicists kind of tailor their current work and their resumes to sort of meet what's the term, meet the puck where it's going to be, not where it is, right? James, what do you got?
In my opinion, I've seen kind of like off-the-shelf solutions from companies really get to much more maturity nowadays, and a lot of data scientist jobs, it's just learning how to link these existing pieces together. They're relatively well polished. They're not as developmental as they were 5 years ago. You still are from time to time writing your own custom ML algorithms to do something fancy that maybe your software that you're using at a particular company doesn't support. But it does feel like you're starting to see more knowledge with specific named tools as being like your day-to-day kind of thing that you're doing. And open source is still hugely common, but that's matured as well too. It's just a lot more mature. It's not so much the Wild West anymore as it was several years ago. That's what I see as like kind of the biggest change over the past couple of years.
I agree, and I'll add on to that I think one way that researchers, astrophysicists, et cetera, can aim that direction is not only, like I think James was kind of pointing to, like learn those fundamental tools, but the things that are harder to automate and buy off-the-shelf tools are that data cleaning and understanding and telling a good story with data. And so that's, I think, like we've heard a couple times, one of the reasons why astronomers tend to be very good data scientists. And so definitely honing those skills, having those good stories to tell of how you got some data, you cleaned it, you found something interesting, you presented it to people, et cetera. That I think that's going to be the more unique thing, and will continue to get even more unique going forward. People that know how to run an NLP or whatever regression model, more and more people can do that, and it's easier to do that with time. All right, Taka was moving toward the front, so I bet he has something to add. So yeah, feel free to jump up here.
So yeah, I agree with those points, and along the same vein, there's a maturation, and that goes hand in hand with an expectation of some of the knowledge around some of the tools. So when I left for data science, say 6 years ago, if you knew how to build a machine learning algorithm and you had a PhD, you might get hired as a senior data scientist right away. Now that person might be a junior data scientist or data scientist. Senior data scientists nowadays are expected to know things, basics of ML ops, for example, knowing like tools like Docker, or knowing your way around some AWS or an equivalent in Google Cloud. Like it's like, oh yeah, I know how to like build, a container and upload it to the repository. I know how to build pipelines around the model. Those are kind of the things that like previously, like if you knew 1 or 0, they're like, okay, if you know how to model, we'll teach you the rest of our workflow later as we train you. But now there's so many tools. It's like, well, there are about 6 or 7 tools we use. It would be nice if you knew like 3 of them or the, an equivalent across platforms. So there's this, as data science has gone from more of like, hey, build us an algorithm, to, hey, deploy it in our business. And there's much more of a focus on the latter. And so knowledge around platforms, knowledge around deployment practices is becoming increasingly more important even for relatively junior roles.
Yeah, I feel like there's.
I just
Sorry.
wanted to make sure we're going to take a little bit of a break now. We've got some lovely new snacks and fresh coffee and soda. I think we can certainly continue the discussion a bit. We have talks starting again at 2:45. So. All right. I was having snacks and losing track of time. So thank you guys for reminding me and bugging me. So, okay, we're going to have our last couple of speakers here. So just if you want to do introduction, and I will pull up the talk on our side.
Sounds good. So these are our last two talks of today. The first speaker is Himanshi Sharma, a graduate research assistant at University of Idaho. Fun fact, we share the same PhD advisor. And she will be speaking to us about machine learning on spectra data. So
And we're
once you're ready on your end, feel free to go ahead.
All right, hold on. Third time's the charm. Screen share. We can do this. Share.
Is the link that station?
No, it should be okay. Did you see? You stopped sharing. Okay, hold on. Let me make sure I have it up. Okay, so that's what we want to share. We can do this. Everybody believe. Sure is loading. No. Okay. This is what we want to do. Does that look good on the Zoom side?
Looks like you just need to go into presentation mode.
Yep. Getting there.
Excellent.
Huzzah.
Thank you.
Hi, everyone. I am sort of the odd one out of the well-established speakers because I'm still a graduate student, just transitioning into data science. I taught myself machine learning last summer by reading hands-on machine learning books and taking online courses. When the summer ended, I had learned some basics and I thought I could probably apply this to the data or the research that I'm doing for my PhD itself. And that's what I decided to do. And that's how I ended up with this project. I'll start with specifying the problem that I'm trying to solve with a little background on the specific data that it is. Then why we use a machine learning algorithm to solve this problem to the specific data set. Then how we apply and choose a model, what changes we make to the model or the data. Finally, conclude with the results and discuss further applications. One of the goals of this project was to demonstrate that I can spearhead a machine learning project and show my skills. What is the problem we are trying to solve? So Enceladus, the moon, it's the 6th largest moon of Saturn. Enceladus is mostly made of fresh, clean ice. NASA's spacecraft Cassini discovered that geyser-like jets spew water vapor and ice particles from an underground ocean beneath the icy crust of Enceladus. More than 100 jets have been identified on the south pole of this moon. So this is a picture of the south pole of Enceladus, and you can see the plume coming out, being ejected out. What makes this moon special and unusual is because it's geologically active. We are trying to understand how this material is being ejected out. What is happening beneath the surface? How is the subsurface ocean working? So that's the problem. The solution to this problem is an application of machine learning. We are going to apply an ML algorithm to a unique data set that's noisy. Real astronomical data, as you all know, has a very low signal to noise ratio. Let's see how we do that. Before we go further, let's get a little bit of background on the plume. So this plume, Enceladus' material that's get ejected out, varies on a number of time scales. One of those most important variations are periodic. Enceladus moves in a slightly elliptical orbit around Saturn. This is an exaggerated version of that orbit. On both sides at the bottom here, you see low resolution WIMPs images at the epicenter and the pericenter of the orbit. What is WIMPs? WIMPs is a visual and infrared mapping spectrometer that was on board Cassini that explored Enceladus in detail. These images are at a particular wavelength. What we observe is that more material seems to be escaping when the moon is farthest from its home planet, because the cracks at the bottom of the South Pole are pulled apart because of the tidal stresses it experiences. So that's the science behind it. And when it gets closer to the planet, those cracks are shut. So that's why we see more brightness at the epicenter and less brightness and less material at the pericenter. In this image, the blob that you see is Enceladus, the moon. On the South Pole, we can see the material that's coming out. The data that we are looking at is from WIMPs. This GIF here is a transition of the moon in its orbit around Saturn. The white blob in the center, is situated at 0 on both axes, is Enceladus. The negative y-axis shows the distance from the South Pole. And the different images in the GIF show the orbital phase. What is orbital phase? Orbital phase defines the position in the orbit. So we see that the plume increases as we reach an orbital phase of 180 degrees. 180 degrees is the position where the moon is farthest from Saturn. So this is demonstrated that the brightness does increase that when the moon gets farthest from the home planet. I'm going to answer a question here that you might have, that this is imagery data. I basically have images at several different wavelengths. So could I use a convolution neural network to try to solve this problem? So we are not trying to study this image as a whole. We are focused on very few pixels, and we want to understand how these pixels change across different scales. That is, across the y-axis, from one orbital position to the next, and from one orbit to the next itself. So we are only concerned how the curve changes from one image to the next. So it isn't exactly image data. It's more like image data converted into numerical data. On the other side here, you see the plot for the 3 different orbits that we are studying. The different orbits are June 18th, August 2nd, and August 28th in 2017. On the y-axis, you have the plume brightness, which suggests the material. On the x-axis is the orbital phase, which defines the position. For all 3 orbits, you notice that the material or the brightness increases around the epicenter of the orbit, but it does vary from one orbit to the next. Could this be related to the size distribution of the particles that exist in the plume? And could they answer the science question about how this material is ejected out or how this ocean seems to work? To understand these particle properties, we take spectral data that we specifically discuss. So you just saw the GIF of the images. That was at one particular wavelength. Usually, when we deal with image data, we have 3 channels, RGB. This is hyperspectral data. We have about 352 wavelengths, which are very noisy. Besides just carrying null values, there are so many outliers too. So we bin this data, apply multiple median filters on different scales, try to improve the signal to noise ratio. And after doing that, these are the results we obtained. What is going on here? The three different orbits are shown in different panels. On the y-axis here, equivalent width is basically the integrated plume brightness, which again refers to the material that comes out. On the x-axis, we see the different wavelengths that we have binned. Why is spectra usually studied? From spectral data, we try to gain mainly two important pieces of information. One is the composition of the material. Second is the size distribution or the size properties of the particle we are studying. With respect to the composition, all three curves for different orbits at very similar positions in their orbit and distance from the south pole of Enceladus show a water ice absorption band around 3 micron, if you'll notice. That defines the composition because we know it's icy particles. We know there's water vapor. The shape of the curve around the water ice absorption band defines the size properties, defines the maximum radius, the average radius. And the shape of this curve seems to vary when we go from one orbit to the next, or when we change orbital phase, or when we change altitude. And we are trying to understand those variations, make sense of them. How do we usually solve this problem? When you want to understand a spectra, you compare that spectra to theoretically generated models. Me-scattering theory is widely used to compare these spectra. So me-scattering theory generated spectra can help us derive information about particle sizes. So usually we'll solve this problem by comparing this theoretical spectra to your observed spectra and maybe do a chi-square fit, which we did try to do for different size distribution parameters. So what we did was generate tons of me-spectra, over 1,000 models for different size distributions. What kind of size distribution? A power law size distribution, which is defined by a minimum size, a maximum size, and a power law index. 4 examples are shown here. As you'll see from the index, the bottom plot shows you what the size distribution looks like, and corresponding to each size distribution, you have a different spectra. The theoretical spectra is different for each of them. Each of them has a different slope, has a different shape. When we try to solve this problem analytically and just do a chi-square fit, it's very difficult to obtain a solution that converges, an exact solution. What's even more difficult is getting uncertainties on those points. So we thought perhaps we can apply machine learning to this data. And because I had just learned new skills, I wanted to apply them. Why do we use machine learning here? Because of course, there is a large parameter space to explore. Like I said, more than 1,000 me-spectra or theoretical spectra were generated for several different size parameters. We wanted to compare all of them. Some of these spectra are very similar to each other, even when we change the properties, and some of them are radically different. A machine learning model is capable of recognizing those patterns and relate them to a complex model that will determine the best fit, that will determine which theoretical spectra and which observed spectra fit the best together. And a machine learning model can be made robust to noise or fluctuations that may exist. How do we do that? So the theoretical spectra that was generated using me-scattering theory was done using a Python package. This Python package generates perfect data. There is no noise in it. There is no chance of error. If we were to generalize our model, if we were to train our model on this data and try to make predictions on very noisy, realistic observed plume spectra, it will not generalize well because we did try it and it did not generalize well. So we decided that perhaps we need to make our training data as realistic as possible. How did we add that noise? We came up with a couple different options, but decided on this. So, you know, the plume or observed spectra had so many error bars on it that it had been binned on different scales. So we knew that these plume spectra have a certain standard deviation or errors on them. We multiplied that error with a random standard normal distribution and added it to our me spectra to create realizations, make it as realistic as possible. These are the 4 examples of the spectra you just looked at that were perfect. The black line here shows the me spectra or theoretical spectra without any noise in it. All the colors show the realizations we created by adding noise. So for each labeled data, because the theoretical data is labeled, we have multiple observations now. So we have increased our sample space, given the model more data to train on. Data augmentation has been applied. After we have obtained the data, decided how to make our model better, we need to decide which features to use. This problem was unique in the sense that which features to use were not clear to me right away. It's maybe because I'm a newcomer, but we had trouble defining the feature set itself. One of the options, how you understand the size, is by studying the curves beyond the absorption band, right? That's how you understand sizes. So we decided that we'll apply a linear and quadratic fit on both sides of these curves and use those parameters as our features. Second option was to use all of the brightness values, the whole curve, as your features, as your columns. So each wavelength, the brightness at each wavelength would be your set of features. Comparing these 2 models, of course, the second option did better. I mean, it's obvious now, it wasn't obvious back then. Why? Because the second option takes into account the absorption band. So it's taken into account the whole data set, the whole curve, so it does do better. Now we know what data set we are using. We have improved it. We have done data augmentation. We compared about 15 models. I've shown just a few of them here to decide which ones we are going to use for our problem. On the y-axis here, you see the cross-validation root mean square error. On the x-axis, there are different models. By looking at it, you can see that random forest and k-nearest neighbors do well. There were other models too, but I only showed these because they're defining how much of a difference exists. Now you would think that because random forest is doing better, that we would choose that algorithm. But we made a conscious choice to use k-nearest neighbors because it was so much faster. I mean, yes, it is faster. And after applying some hyperparameter tuning, we were able to improve the accuracy. The root mean square errors could be further reduced, and it came to the level of random forest. I mean, the difference was already low. So we decided to use k-nearest neighbors as a machine learning algorithm on our data. After using a machine learning algorithm, we decided that perhaps we can even try a deep neural network and see if the accuracy improves by a large value, if it makes a huge difference. Because a complex model can understand non-linear relationships, and our data is indeed complex. With k-nearest neighbors is so good that the root mean square error or the R-squared value, because it's a regression problem, were very similar to one another. So we do trust our KNNs. To summarize, how I did this problem was generate lots of theoretical spectra for a range of size distribution parameters, added Gaussian noise to it to make it realistic, split the data as one would usually do for an ML algorithm, trained the nearest neighbors on this data, checked the accuracy, did some hyperparameter tuning, improved the accuracy, and used that model to make predictions. Do these predictions make sense? So in these plots, we have overplotted our observation with the results we obtained from the machine learning algorithm we applied to see if the model actually worked or not. The black lines show the observed plume spectra. You'll see that it's noisier. The three different colored lines show the three different orbits we were studying from June 18th, August 2nd to August 29th. The three different orbits show that the three different lines in color show that they are reasonably good fits to our black noisy data. So the machine learning algorithm did work, and we believe it's a trustworthy solution to this problem. Yay! Now that we have the target labels for our data, of course, we wanted to try to answer the science question. I mean, we leave the heavy modeling to the modelers, but from some basic calculation, because our size distribution parameters were already obtained because we have made predictions. So we use that to calculate the average radius or average size of particles. We know how it changes across three different scales: across altitude, that is the distance from the South Pole, across orbital position, and across different orbits. We don't know all of the implications. We're still working on that. I wanted to share this result with you for a reason. You'll notice that my observations have error bars on them. A machine learning algorithm just gives you root mean square error. How did I get different error bars on all of them? So you remember how I applied noise random standard normal distribution using the error bars on the plume spectra that we did on the training data. We did the same thing on our observed plume spectra. Why? Because we already knew that they exist in a certain range. I had the error bars for them. So why use only the average? We created realizations for the observed spectra too, knowing that it exists in a certain range. Because of which the predictions on all of them combined were able to give me an error bar. Doing this change or data augmentation to our prediction data set did help us obtain these results with error bars and did converge our results too. Otherwise, the model sometimes gave different results and it felt like it is not converging. We also compared these curves to the solutions obtained using random forest and a deep neural network just to see how much of a difference it's making. They are all the same. They are within the error bars of each other. So we trust this algorithm. So this is an regression problem. I wanted to point out that this model or this technique can be applied in a classification problem too. So for regression, we are studying size. For classification, you could study composition. For regression, your output was, size distribution parameters. For classification, your output can be whether a certain material exists or not. We hope to extend this solution to classification problems too and deploy the model eventually when the paper gets published. To conclude, I would love to connect with people who are at the cusp of transitioning into data science like me, help each other interview prep network. So please come talk to me. Thank you.
Got time for a couple of questions. I'll ask one. How much data do you hold back for training versus validation, etc.? What was the split there?
It was an 8:2 ratio because I had millions of rows after applying data augmentation, so it was enough. Yeah. I know it's a very science-heavy talk.
I'll ask a question. I thought it was really neat that you were able to add the noise to the data to help you train it better. I'm just wondering if there were any assumptions that went into using a Gaussian fit for the noise, or is that something that was thought through, and like, are there good reasons to assume that it would be Gaussian, or? What was that thought process?
One of the reasons, Joseph, was a model. When we apply data augmentation, my understanding is that the noise that's added should be understandable by the model. It should make sense. That's why when we applied Gaussian noise, we multiplied it with the error bars from the plume spectra. So it was as real as possible. But it was mostly standard because, standard normal distribution is what's used. Often for data augmentation, the second reason, like I said, we want the model to be able to understand that noise.
Right, thanks, Himanshi again.